All right, Chapter 7. Section 7.1, or let me go ahead and title Chapter 7, is on energy. And Section 7.1 has to do with defining your system. So we've already talked about this a bit in class and in previous sections, but a system is the way to separate the object of interest or objects from the environment, right? And this can be an object or a set of objects. And it's important to understand because we're going to be talking about work, which is section 7.2, at least, is work by a constant force. So the distinction here that we want to make is work done on the system, work done by the system, and you have to identify how energy is transferred across the system boundary. Well, one of those ways is work. So we're first going to look at a constant force, and then we're going to look at how to expand that to a varying force. So remember, force is a vector. So that means magnitude and direction. And that means when we mean that it's not varying, that means that the direction is also not changing. So work is defined to be I'm going to use R because that's what your textbook uses for displacement in this section. So we have work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of theta, where theta is the angle between the displacement vector and the force. So if we look at it this way, we could have something like this. All right, so we want to kind of consider how changing the angle impacts it. And I guess I've already given you equations so we can guess, right? Imagine that I pull straight up on the block with a force that's less than its weight. Then it doesn't move, right? If it starts at rest. But what if I pull at some angle? Right? If the force is large enough to overcome the static friction, it will accelerate. And if I pull at some other angle, if the force is greater than the static friction, it will accelerate. And the question that we ask is, what force is most effective at moving it? Right? If these are all the same magnitude force, right? Well, let's assume that there's no friction here, because if there's friction, that can complicate it, right? If there's no friction, then this is the most efficient force at moving it, right? I'm going to note here that we're saying no friction. All right, and we've already had that revealed from the equation of work, right? If we look at the equation of work, let's plug in some values there. If I look at the first scenario I had, well, we're trying to move it along the ground, right? So if I look at cosine 90, that's 0. We can just call this 45 for the second scenario. And so quarter root of 2 over 2, all right, would be our cosine 45. And then for the last scenario, they're in the same direction. Cosine of 0 is equal to 1. So if the displacement is the same in each case, and the force is the same in each case, then the work is going to be the largest for the one that's in the same direction. All right. We've got 0, something less than 1, and then 1. All right, what else do I want to say from this section? Let me double check the book here, see if I haven't missed something obvious. Okay. We've talked about angles between 0 and 90. Let's talk about one greater than that. So let's say the block is sliding along the ground, which if we had some displacement, we did need an initial velocity for this one, right? Because it's not doing anything to the block. And we're now going to apply a force like this. So what does that look like? Well, it still had a displacement in this direction, but now a force in this direction. I've already labeled it delta x. So this is a theta that's greater than 90, and cosine of theta, where theta is between 90 and 180, is negative. So we're going to get a negative value for the work here. What actually happens to this block if we have a force that's acting opposite the direction of motion? It's going to slow down, right? And that's what a negative work means, is that we're taking energy out of the system. Positive work adds energy to the system, and negative work takes energy out of the system. And that's taken care of in this equation. I think that's all that I want to say for section 1 and section 2. Section 3 has to do with the scalar product, and we're going to get into a lot of mathematics on that, so I'll do that in a different video.